Hi, I'm Ben Newland at Cardiff University, and last week I was interviewed by Dr. Aya Tarabeine from the Your Brain Uncovered podcast. It was really interesting and engaging conversation, and so I thought I'd share a small excerpt of it with you here. And it's about our latest lab project, which is using the cryogel scaffolds that I mentioned in my last YouTube video as an implantable device. So it can be implanted into the brain, specifically into brain tumors. And by doing this, it means that we can then repurpose existing drugs that can't actually reach the brain, but by implanting them directly there, we can get them to deliver the drugs directly to the tumor site. So this opens up the doors to using a wide range of therapeutics that are currently available, but that can't reach the brain. So if this is just a small clip of that podcast, and if you would like to see the full interview, I'll include a link to the podcast below.
Dr. Newland, welcome to the show. It's a pleasure to have you here.
Yeah, thank you very much. Thanks for having me on.
Thank you for being here. I believe the question kind of begs itself. Given your background training in materials sciences, how come you decided to dedicate, the application of your research to using the brain?
It was about the time that I started my PhD. It was just before that, actually. My mother got diagnosed with Parkinson's disease, and the group that I joined to undertake my PhD, the supervisor on the first day said, basically, these are the polymer materials we've got available, and you can pick which direction you want to take this research in. And so it's an amazing opportunity, really. He just says, we'll work with other people across campus to make it happen. So straight away I thought, well, I definitely want to work on Parkinson's disease. And so this is really where the marriage of the material science and the polymer chemistry work fitted with, really what's carried on being my interest in the brain, even though it's not just Parkinson's research anymore, as obviously we're going to find out about. But that's really where it stemmed from.
All right, that's lovely. So there's plenty of opportunities for you to be working on that in the future, I guess. And please do correct me if I'm wrong, but so what you're currently focusing on is really investigating various delivery materials and optimizing the formulations for drug delivery, as I suppose. And your work has mainly focused on using highly porous hydrogel scaffolds. I believe they're termed as cryogels.
Right,
I'm no expert, obviously, so would you be able to please explain what are cryogel scaffolds exactly?
Great. No, I mean, these form the mainstay of our lab. If I'm honest, they're our bread and butter, and it's where I'm trying to place a lot of our expertise. So what are they? So these are the materials that we're using to deliver, that we originally developed to deliver cells to the brain for the Parkinson's disease project. And then we sort of noticed that and we modified them so that they'd be good at delivering proteins to the brain, things like growth factors, which support neuron survival, okay, all in the Parkinson's field. And then we realized that the same concepts that apply for that apply for drug delivery too. So that's where that came into. That. What are they? The easiest way to think of them is like a sponge. Okay, so they're like little sponges, and we make them in, as you alluded to in your introduction, we make them in different sizes. Some of them are macro scale; they can be 2 or 3 millimeter in diameter, and they can be like a little cylinder of the sponge, and all the way down to the smallest ones we make at the moment are 20 micrometers in diameter. So very, very small spheres, basically little balls of sponge.
And I'm just as curious, would you be able to please elaborate more on their characteristics and what makes them stand out from other current modes of delivery?
The reason they're so interesting is that the properties of them are from the macro scale. If you imagine picking up a sponge and squishing it between your hands, right, it feels very soft. Yet the network that's building that is, I wouldn't say it's stiff, it's definitely not stiff, but it's very robust. Okay, so the easiest way I can try and describe why that's important is obviously because our brains are very soft. Okay, so not obviously, maybe that's not obvious to everyone that hasn't taken apart a human brain before, but if you have ever had the opportunity, or an animal brain, you'll realize that they're very soft. It's very soft and squidgy, right? And so a lot of the delivery devices that have been developed have been hydrogels, and a hydrogel put simply, is basically like a jelly, just like jelly on the plate, or in Americans I think are called Jello, I'm not sure. And so it's like this soft substance. But the problem with jelly, for example, is it is very soft. We can make it match the human brain in terms of its properties, so it's well accepted in the brain, but it will dehydrate. If you leave jelly in the sun, it'll shrink down to a sort of a flat, sticky mess. And if you put water on it again, it won't rehydrate back to the same shape that it originally was made. All right. So they're also quite difficult to inject if they're ones that form once they've been injected into the brain, because they rely on temperature and things like this. And definitely people have got better and better at it. But it's that sort of route there using hydrogels is susceptible to the things that you need. The surgeon would need to be trained in it very well, understand the materials and things like that. The work that we're doing with the cryogels, which are basically, I didn't really explain where the term cryogel comes from, but it's basically a hydrogel that you make and you put it together inside a freezer. Okay, so the cryo comes from the word ice, from Greek. Okay, so the ice crystals form within that jelly mix, basically in the freezer. And that means that you get these big pores, these big holes all the way throughout it where the ice crystals were. They're pure water, more pure ice. Okay, and so around them, the polymer network forms. That means when you defrost it, you get left with these big pores and things like that. So just like a sponge, on the outside feeling in, if you put it into the brain, what the brain feels macroscopically is a very soft substance. Yet all of those little lines and the bits that are holding the sponge together, all of the network around that, what we call the struts, are very robust. So they can be picked up with a pair of tweezers, they can be moved about, they can be dried, just like a normal sponge, and then they can be re-wet with the drug, okay? So it means we can sterilize them and things like that. So it makes it, looking forward to clinical use, makes them very easy to use and very practical in that aspect. And there's not, the reason I get excited is because there's not really many materials out there which are so, can be tuned to be so soft, yet it's remarkable that you can pick them up with a sharp pair of tweezers and they're not falling into bits, if you see what I mean. That's where that dual characteristics of soft yet robust is what I find interesting. And of course, we can change the chemistry to help suit slow drug release and things like that.
Here, so you kind of describe the characteristics of this, a sponge-like gel, and what I do get is that it kind of compresses and reshapes to take in, the shape that we want, which makes it really easy to inject. And obviously, the cryogel microcarriers have been applied to several other areas of research, which is quite nice. But in terms of practicalities, what do these cryogel microcarriers actually have greater therapeutic potential, in comparison to systematic drug administration? Because, that is kind of the golden standard in a sense when it comes to brain cancer. So would you be able to explain this?
Yeah, sure. So firstly, as I alluded to, there's this problem of the blood-brain barrier. So currently, the standard of care is to give a drug called temozolomide. Now, if you grow cancer cells in a dish and you give them temozolomide, they're not overly harmed by it. They are. It depends on the dose. Everything's, it always comes down to sort of dose responses and things like that. But if you give them, there's a wide variety of other chemotherapeutics that you can give them that absolutely hammer them. They're really, really potent and will really destroy both the cancer stem cells, the glioblastoma stem cell population, and the rest of the tumor, right? We know that they're much more potent than temozolomide, but temozolomide is used because it's one of the few that does actually pass the blood-brain barrier. So coming back to answering your question, could local intervention via the microcarriers be, better than systemic administration? Well, the answer lies in the fact that you could now target multiple mechanisms by which the cancer cells survive, by which they migrate into the rest of the brain. Okay, they actually switch between the type of cell they are. They're incredibly clever. They switch from looking like a neuron to going back into a mode where they will rapidly divide, etc. So I think by this strategy, it gives us the opportunity to dose multiple drugs at once, Also use drugs that can't pass the blood-brain barrier. And lastly, but really importantly, is you can give a relatively high dose to the tumor without it affecting all your peripheral organs. So there's this problem, obviously, with chemotherapeutics, as you know, as we know about in breast cancer, with hair falling out and everything else, is that the side effects limits how much dose you can give to the tumor, because the person's obviously going to become too sick. So if you can deliver them directly to the site, you can deliver a high payload without it affecting your liver, your kidneys, everything else, right? So I think those are the advantages of it, and I'm really excited by the prospect that I think this could have a real step change in how we treat brain cancers and other cancers too, for that matter, with local therapeutics. But there's a long way to go in terms of getting that release right. If you just release all the drug in the first day, for example, that might be great for certain aspects of it, but if you're really trying to encompass all the different ways that a brain cancer cell can survive, I think we need to have a slow release over a long period of time that can target this in multiple different ways. And that's not an easy part. To get that release right is the focus of my two of my PhD students at the moment in the lab. That's really what they're doing, is tailoring these to give longer and better and flatter release profiles. So it's not all just a big burst at the beginning and then all over.
Dr. Newland, thank you so much for your time and for all the work you've been doing. Honestly, we really look up to you. And for all you listeners out there, please feel free to check out his academic profile, and feel free to reach out on Twitter as well, because I provided that in the show notes, as mentioned earlier in the episode. Is there any last words you'd like to leave us with before we end this?
No, I don't really. Just to say thank you very much for having me.
Anytime. It's a pleasure. Thank you. Thank you for being here. And for all you listeners out there, please feel free to leave a review and subscribe wherever you listen to this podcast show. And thank you again for listening. And more importantly, thank you for your interest in science. Goodbye.